Hello students, welcome to another tutorial on mechanical properties of matter. In this video, we continue looking at fluids at rest, and then we start right ahead by looking at a question I left you guys with in the previous video. So the approach we're going to take is similar to the one we used in the previous video. The key difference here is the fact that the cross-sectional areas are different. So we're going to see exactly how that affects our calculation. In the first part, they want us to find the solution of the water. Not the solution, sorry, they want us to find the length of the water column in the right arm of the U-tube. So that is this part here. So this is the column of water that has been added. Let's see what we're given. So the question tells us to say that we have the cross-sectional area for the tube in the A1 part, that's 10.0 centimeters squared. And then on the right-hand side, what we have is area 2 given as 5.00 centimeters squared. 100 grams of water, so the mass of water being added here is 100 grams, and then this is poured on the right arm. Okay, we've got that. Now let's see if we can find the length. So yeah, so I hope you guys do recall your expressions of pressure from earlier studies, but what you should keep in mind is pressure is given as force over area. So pressure is given as force over area. But then in this case, what we want to find is the length of water given the cross-sectional area and so on. So we might not really even touch this formula. Now we know the density of water. The density of water is, since everything has been given in grams and in centimeters, the density of water, we're going to take it as 1 gram per centimeter cubic. So why do we need the density? Well, we know to say that density is equals to mass over volume. So I want to get the relationship between mass and density. And then from here, I can then relate this. I can use this to get the expression for volume. Volume is equals to mass divided by density. And then we recall, if we have some section like this, if this is this has some cross-sectional area here and some height h, to get the volume of this particular shape, all we have to do is multiply the cross-sectional area at the base by the height. This will give us the volume. In other words, this is true for our column A1. So we can just multiply. We can just equate this to the cross-sectional area A1 and the height. So we see that this part of our expression gives us the area, the height h, since we know the area A1, we know the mass we have to deal with and the density. Now, so we only have to write this equation in terms of h. So this becomes the mass, the density, multiplying the area A1. So when we perform our substitution, the mass of water we're dealing with from the question, we go back, that's 100 grams. So we have 100 grams. The density, we're using 1 gram per centimeter cubic. And then this is multiplying the cross-sectional area. A1 is 5 centimeters squared. So if you simplify this, including the units as well, this reduces to give us 20 grams, not really 20 grams. The masses will cancel, the grams will cancel as well. So the only unit that will remain is going to be a centimeter from here. 2 will cancel with the centimeter squared there. The gram will go with that. What to remain with is just going to be 20 centimeters. So this becomes the height of the water column added on the right-hand side. Now let's move on to part B. In the second part now, what they want us to find is, so they want us to find how high the water rises on the left arm. So let's see, given that the density of mercury is at what distance h does the mercury rise in the left arm? So this part here, this is what they want us to find. So I'm going to label this as h. Now here, what we're going to do is, first, we're going to go to the left side, the earlier diagram, and then let's say before adding water, we had the height of mercury, this side x. And since from the diagram, it shows that these, initially they were of the same height. So I mean that even on the right hand side and the right arm, this was 2x. But now, after adding water on the right arm, we see that the height of mercury on the left arm increases by this factor h. But on the other hand, on the right arm, on the left arm, it increases by h, but on the right arm, it reduces by some height. So this reduces by some height. Now, in the previous example, this side reduces by some factor and it increased the other side by the same factor. But because of the difference in cross-sectional area, these two quantities will be different. So I'm going to label this as H2. So let's say, let me actually just use H1. So on the right-hand side, the height of the column reduces by H1, and then on the left arm, what happens is it increases by h. Now let's see how our expressions will look like in this case. So first we identify the pressure which is acting here. So first we have the atmospheric pressure, that side, but then since this side is open as well, we also have the atmospheric pressure this side. And then apart from that, we have the pressure due to mercury going down, we have the pressure due to water here, and then we have the pressure due to mercury this side. So you can take the pressure at the bottom now to be the pressure here, the pressure there. So the pressure, atmospheric pressure plus the pressure due to mercury on the left arm to be equal to the three pressures on the right arm. So that's one way you can take it. Or you can say, since this is in equilibrium, as in this above we're saying it's fluids at rest, you can just start from this side, start going down. So you're saying if you're in the same direction as your arrow, positive, positive, when you find the arrow which is in the opposite direction, negative, 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 and then equate to 0. That's one way you can look at it. So I think that method is kind of easy if you're still struggling with how to really equate the pressures and so on. So start from one arm of the YouTube. It doesn't matter whether you start from the left arm or the left arm or the right arm. It doesn't really matter. Just start from one. If you're going the same direction as your arrow, positive, positive. This is now in the opposite direction, negative, negative, negative. Okay, so if I use that approach, first we have on the left arm, pressure, atmospheric pressure. And then after that, we have pressure due to mercury. So that height, remember, it increased by that factor h. So it's x plus h. And then this, the other side, if I use the part where the arrows which are opposite give me a negative, so I'm first going to find the pressure due to mercury, which is going to be rho m g. And then this side now, remember, the height reduced by h1. And then next, I find the pressure due to water, also opposite direction. So that is just rho water g. Now the height of water is, we adjust from finding the height of water in the previous question. So that is 20 centimeters. Now I'm using 20 centimeters because the density of mercury is given in grams per centimeter cubic. So even the density of water, I'll use it in grams per centimeter cubic. And then lastly, the atmospheric pressure on the right arm, also negative, and then everything equates to 0 since these fluids are at rest. So this term quickly subtracts with this term, and then you move the other terms to the right hand side. Okay, you can start simplifying from here, but I just want you guys to see that this just comes to look like our earlier approach for just equating the pressure on the left arm and on the right arm. So if you just took that approach, equating the pressure on the left arm to the pressure on the right arm, you should see that you would have ended up with this exact expression. Okay, now at this stage, we see that every term has gravity, so gravity quickly cancels out. So after we cancel out gravity, what remains? So we see that once we cancel out gravity, now what we have is rho mercury, and then x plus h equal to rho mercury x minus h1 plus raw water, then the 20 there. So from here, I can expand this. So this becomes raw mercury x plus raw mercury h equal to raw mercury x minus raw mercury h1 plus raw mercury, this is not mercury, sorry. So this is water, 20. So from here, you can see that when you group the like terms, this term and this term are going to subtract. So I can move this term to the left-hand side of the equal sign. You see that it becomes negative. So this and this will quickly cancel out. So you remain with raw mercury H is equal to negative raw mercury H1 plus raw water 20. Okay, now from here, what we want to do is, you see, the question gives us the density of mercury. This is given as 13.6 grams per centimeter cubic. So we're taking the density of water to be 1 gram per centimeter cubic. So how about that H1? Well, we don't know what H1 is, but using our earlier relationship, we know that volume can be written in terms of area A1. If this is V1, then this becomes area 1 times H1, implying that H1 can be expressed in terms of the respective cross-sectional area and volume. So this becomes, that's going to be volume V1 over the cross-sectional area A1. Now, one thing I want you guys to keep in mind is, well, I want to know what I have to put this side in terms of this equation. I know I'm going to substitute this expression where I have H1. I'm still going to have a problem with V1 here because I don't know what V1 is. But what you should know is, what you should keep in mind is, see, on the left arm of our column, let's say if this is what we had. Okay, so you see, the volume of mercury that is pushed down, that is the same volume of mercury that is going to go up this side. The only problem is, on the right-hand side, it ended up having a large value of H. But on the left-hand side, the height ends up just being something a little bit small. But the volume you're dealing with is still the same. The only thing that changed the height is the fact that the areas are different. So that's the key thing that you have to get. So in other words, the volume on each side, it's the same. Here we have V is equals to A1 and H. The other side, what you have is volume is equal to A2 and H1. So here I labeled the height as H1. So you see that H1 will be given by V over A2. And then on the left arm, you see that H is going to be given by V over A1. So when you perform our substitution into our equation, let's say this is our equation 1. So you see that now what we have is raw mercury, and then we have where we had H, we're going to substitute this. So this becomes V over A1 equal to raw mercury, and then we have V over A2 plus, okay, so this term is negative. Let's just confirm from equation 1. Yeah, that term is negative from equation 1. So plus, and then for the term that from the water term, so we have this, and then the H here, we know what the H is, so we don't have to express it in terms of volume and area. Okay, so from here now, all we have to do is to work out this expression for volume, group the like terms, perform your substitution. So we basically have raw mercury, V over A1, plus raw mercury, V over A2, is equal to raw water 20. So just move this term to the left-hand side. So when we perform our substitution, what we now have is 13.6 V over 10 plus, and then this side, what we have is 1. This just become V, since the density of water. This is sorry, this is not density of water, this is mercury. The density of mercury, that's 13.6 V over 5 equal to, this is 1, so this just becomes 20. So when you simplify here, what you're going to have is 1.36 V plus, and then this side, what you're going to have is 2.72 V is equals to 20. And then when you simplify, this becomes 4.08 V is equal to 20. Work this out for V. Divide both sides by 4.08. This reduces to give you V as 4. Okay, so this becomes that's 4.90 centimeter cubic. So this is the volume that gets to move down on the left arm and up on the right arm. But what does it mean in terms of length on the left arm? So we relate volume is equals to area times height. So on the left arm, this is now area 1 to find the h. So this implies that h is going to be equal to volume over A1, and this will be the volume 4.90 centimeter cubic divided by the area on the left arm, that is 10 centimeter cubic. Okay, sorry, not centimeter cubic, this is centimeter squared. So when you divide, this gives you 0.490 centimeters. Okay, so this is the height of the mercury column that goes up on the left arm. So I hope you guys were able to get the key difference and the key approach here. Because of the fact that the cross-sectional areas are different, we had to recall that the volume that is pushed down here will be the same volume that is going to go up here. The only thing is the heights will be different because of the cross-sectional areas. So the cross-sectional areas will affect how these volumes are actually presented in terms of height. But in terms of quantity, the volumes will still be the same. The volume pushed down will be the same as the volume that will go up on the other side. Okay, so I hope you guys found this helpful. If you did, leave a like. Yeah, otherwise leave your reactions in the comment section. Let's see what you guys think about this video. Otherwise, in the next video, we're going to work out 2 questions. These questions are a little bit easy. I hope we'll be able to work it out without exceeding 20 minutes. So we're going to start by dealing with this question, so you guys can try it out in advance. So this is going to be in the next video. And after this, we're going to also work out another question. We're going to look at this one. So you guys can also try this question out in advance. Otherwise, thank you very much. This was your tutor. See you in the next video.